Okay, talked about scoreboarding, Tomasulo. Let's go through another Tomasulo loop example, and I think this one's going to really show you why this architecture is so powerful, because it's going to do something that the compiler, an optimization that the compiler can't do by itself. So let's look at a loop. There are a lot of loops inside of your code. Hopefully you'll notice that by writing it. Let's just assume, just to put up some numbers, multiply takes 4. First load takes 8. A second load will always take 1 clock cycle. This is for caches. Hopefully you remember some caches. You remember caches. Did you do caches, Jordan? No. Not really? Okay, well, for the sake of argument, just assume that the first time you load something takes 8, and then every subsequent one takes 1 due to the way the cache system works, just for now. To be clear, we're going to show clocks for sub, I, and of course the branch not equals. This is a store, double, and the multiply as well. All right, let's go over here. All right, we have notice we still have our 3 adders or 2 multipliers. We have 3 loads. We have the 3 stores because now we're going to deal with store instructions as well as load instructions. What's that? Nothing at all? All right. Notice that this, what do we take out from here that was in the previous one?
Adder.
We took out the branch. Why are we taking out this branch? What did we just talk about that?
Caches.
Branch. You know, G-share.
Nope.
Nope. That's all been flushed.
It's not on the project, so I flushed it from memory.
Oh, but you have to do a branch predictor, don't you?
Yeah.
Yeah. So we're just assuming the branch predictor is correct for now, just to show you how powerful this is. Because after you predict correctly, you can still issue those instructions, right? Hopefully. All right. These are the iterations of the loop. First iteration is these 3, has a branch, we're going to assume it's taken. Second iteration, and then we'll go on from there. Here's our reservation station. Let's go and get started. We issue the first one because there's nothing busy. We issue the multiply because multiply is not busy. Can we issue the store?
No. Oh, yeah, we can.
Yeah, we can. We can issue the store. And we say that the store going to address 80, I'm just putting in address 80 as pretending as that's the value that's inside of R1. All right, just to give an example. The store is waiting on multiply 1 to complete before it can store it. It's great. Can we issue the load? Yes. Yeah. I'm just trying to point to you why this is so powerful. Because let's go ahead and it's like the way I think of it is you just send it out in the field and see what it does, and then comes back and fix it all later. That's what's going on. So notice that the implicit renaming sets up the data flow graph of how this multiply goes to that store. That was the first point, and then we can have our presentations freeze for a moment, which is always fun. Let's oh, I wonder if that's going to come up when I full screen it. No. Nope.
Yeah, that's what I was talking about earlier. There was like a purple circle thing.
So we can dispatch the sub I unit. Oh. Yeah, so from here it's hiding the sub I unit just to show you. And then of course the branch not equal instruction is hiding as well. And then it would take those two, and then of course the load could start executing. All right. From address 72, which was R1 from the subtract, correct. Yeah, so F0, this is the big thing, or something that may help out. This F0 never sees the load from location 80 over here. Notice F, because it's going to be flat out overwritten by the next load as well. F4, we can issue. Can we issue the next store?
Sure can.
Sure can. Why not? Completely detached from computation. We don't care about the register file.
You tricked me.
I did?
You did.
How did I trick you?
I don't know.
Notice the first and second iteration are completely overlapping with one another. They're both in there. All right, we could continue this to the third and fourth iteration, but I'm going to stop and just show you these completing, just to give you a good picture. We said the load would take 8 cycles because it's the first load, so we're going to go ahead and let that take 8 cycles to complete. When that finishes, what's going to happen?
The multiply is going to get it, won't it?
Yeah, the multiply will get it. Who's waiting? Mult1. Note that it is technically dispatching sub I from the next loop iteration, which is fine. We're just not showing it. That would just take something up in here. So the multiply is going to start executing. Load 2 completes, because remember, now it only takes 1 cycle. Who's going to be updated?
Load 2 was the F0 one?
Load 2 was this guy.
Yeah. So the other multiply would start?
Mm-hmm. Well, load 2 is right here, and there's load 2 down there.
Oh, yeah.
Right? It directly, the whole point of this is it directly tells you what data you're waiting for, or where it's coming from. Notice that it's also doing branch not equal. Yep. So we have these two guys executing. Notice you have both multiplies going at the same time, and no one's completing. Right. Next load in sequence. I'm not showing those because I'm just doing the same two. I just want to show you that, hey, look, we could start executing the third iteration at this point if we wanted to.
Mm.
Why can't we issue a third multiply even if we had it? Oh, actually, I did put up the third load. I lied. There's a third load up there.
Why?
If the third iteration of the loop, remember it starts with a load,
Mm-hmm.
so these slides are going to show the third iteration. It would go right up here because that load can start. But why would the multiply afterwards not be issued?
You only have 2.
Yeah, I only have 2 in here, so we can't issue the third multiply. So now we would finally stall. So multiply, then the multiply finally completes. Who's waiting on multiply 1?
Subtract. No.
You mean store, SD.
Yes, store.
So
Okay.
this guy right up here. So he gets basically updated, and now the store is going to complete in 1 cycle. You can issue the next multiply as well. Mult 2 is now going to complete. Who's waiting on that?
Store 2.
Yeah, the other store as well. This is the mult from the third iteration of the loop. And now we can also put in the store, because after mult has been issued, we can also issue the third store because we have a third reservation station here. And let's see, those are going to complete, and then we're done. All right. You see how these loops are starting to overlap as the machine is executing? Also, if you take into account we never really write to F0, so to speak. We just kind of keep it floating with our renaming. I mean, obviously it's going to be rewritten to the register file at some point, but it's never used down here because these are always coming from some other functional unit. All right. All right, why can we overlap? We have register renaming, which provides, basically it provides a different physical destination for registers instead of having to have a very explicit logical registers like you would with scoreboarding or even with your in-order pipeline. You still have to read from the register file. This optimization is called dynamic loop unrolling because you can execute multiple loops at the same time. Excuse me. Also, the reservation stations permit instructions to issue in advance past where your actual control flow is. In other words, you can issue instructions that are further along the pipeline, even though your current instruction, so to speak, hasn't finished executing. You can buffer old values of registers, which totally avoid all your write after read stalls. And another way of thinking of it is the Tomasulo method builds a data flow graph on the fly while it's executing, saying, okay, you need to take this data flow and fill it into this register station. When you get that, flow it over to this reservation station as well. So it really just builds this graph on the fly. All right. Ooh, we're going to be done soon. Great.
Woo!
Yeah. Hold on. Any questions on this? Because when I issue assignment 2, it's really just do assignment 1, but with this instead. We will get into that next week. I'm not going to assign it right now. I'll assign it next week. But that's basically what it's going to be. That's your next homework or programming homework. Anything?
Did you get Bart's email?
Okay, yeah, I can give you an extension. I don't think it's going to, I mean, if you really want one, that's fine, but I'm still going to assign the next assignment at the same time. It's got to be, I can't change that. So if you need, what do you need, till the end of that week or something?
Yeah, that's fine. Yeah.
Okay, so we'll make it, yeah, sure, why not Friday? You gonna be okay with that?
Yeah, that's good.
Okay, we'll
Now
do
I don't have to work on it. It's STEMfest.
That's good. Congratulations. All right, summary 1. What was the big architectural advantage or benefit here? Reservation stations, you implicitly rename it to a larger set of registers, which gets rid of a lot of hazards and basically allows you to just execute the instruction, and then if it needs to be fixed, it will be. If it doesn't, it just goes. This is the big one. It prevents registers as a bottleneck. You're not limited to just 4 registers. You've basically added virtual registers because you're temporarily, instead of having to wait for the register to be written to, you're just waiting for another floating functional unit to complete. So you have more registers, so to speak. Avoids the war and write after write hazards, and allows you doing loop unrolling in the hardware. Something the compiler could not do because it's limited to a number of registers. Not limited to basic blocks. If you need to go beyond branches, you're good to go. Helps with cache misses as well. I don't know if Bart's done caches, but you took my undergrad course, you definitely did caches. So we'll have to do go through caching again, which is fine.
Be a shame if there's a cache project.
All right. What do they really contribute? Dynamic scheduling. Instructions can execute in any type of order, aka dynamically. It's not statically one after another. It's dynamically, it shifts around which instruction is being executed. Registers renaming, a way to get rid of all your write after read hazards and all your write after write hazards. And load store disambiguation. Let's see. I have to look that one up. Okay, sorry about that. These are some of the yeah. I don't know what I was trying to say with that one. These are some of the descendants, but I need to update this bullet point. It's really basically every processor. Every processor since the Pentium 2 that Intel has produced has Tomasulo running in it.
This is the reason why meltdown inspection.
This will be the first step in understanding why meltdown and spectrum occurred. The next step is figuring out how caches work, and then when you combine the two, you'll see why this is a problem.
Dangerous knowledge.
And it's not really, it is dangerous now. And it's not so much that this method has an inherent security problem as Intel messed up, because AMD doesn't have the meltdown issue that Intel does. But they both believe that they have the Spectre issue. We'll get into more details in a bit, but they can't. The way way Spectre works, it's kind of hard to confirm it actually is an issue or not. So it's a little harder. But meltdown's 100%. Like they just show you, hey, look, I can just read what you're typing, even though I'm another program on your computer. Yeah.
So, the scoreboarding thing has the wall and the war, right?
Yeah, and it stalls on
So
those.
if you do a right after a right,
It's
it'll
stall the yeah, it stalls the
is
instruction.
that maybe what you meant with the ambiguation?
Oh yeah, thank you. Thanks. Yeah, because since you've renamed it and you have you've disambiguated the loads and stores, so now you don't have to worry about right after rights.
What was the one time you did have to stall?
You had to stall when all your reservation stations are full,
Oh,
because you don't have a buffer for it. You can't do anything with it, right?
a buffer.
A buffer. I mean, the reservation stations are a buffer. They're just sitting there waiting for everything to get there so you can start. All right, that was it. All right. Wow, we cruised through that. Any questions? I'm glad we're doing this one day a week. All right, here's a question. How bad is the branch miss prediction now?
Bad,
Why is it so bad?
because you're doing things out of order, so you could have done an instruction that's way later, and then blah.
Blah. Yep. We'll have to talk about how we can fix that with this method.
Can we throw a cache at it?
What else would we do? All right. Okay. That's it for the slides. I did assign some homework.
Ooh.
Ooh, let's see if I can go bring that up real quick. Put it up on Blackboard.
So doing next week or next week?
It's due next week. It's bookwork. It's just bookwork.
Well, I guess it didn't take too long to do, except one of them.
So one of them. All right, it is from chapter 3. Come on. Just a couple of problems. I'm just putting it out here so everyone knows. Did chapter 1. That's due tonight. Here's chapter 3, part 1. This is really just scoreboarding and Tomasulo method. 5 problems. I don't know why it says September 28th. It's due a week from today. Ignore that whole. So yeah, back in 2015. Hey, we did faster than light travel, so you should be able to do time travel, right?
Yeah.
That's basically the first project.
It is the
Time
first.
travel.
Yeah,
'Cause
really.
you're like, what?
It fixes so many issues. Okay. Any other questions? Comments? All right. Then that's all for today. I will see y'all next week.
No, I don't have to work on the